pair. So last time we covered Spartan, which is a snark for R1CS based on the sum check protocol. And today we're going to cover Marlin, which is a snark also for R1CS based on something called the univariate sum check protocol, which I think is actually a confusing name, although I certainly understand where it came from, and I'll explain the origin today. So let me just say it's based on univariate polynomials. And actually both Spartan and Marlin apply more generally than R1CS. Although this seems to not have really been fully appreciated till recently, when I put out a paper not that long ago that kind of pointed this out. But they are nice and clean to describe for R1CS, and that's how they were originally described. So that's what I'll limit my description to today. And so let me just explain briefly kind of what the pros and cons of Marlin are relative to Spartan, just so you understand why we're covering like a second snark for R1CS. So I guess the big benefit of Marlin over Spartan is smaller proofs. I think concretely Marlin proofs are a handful of kilobytes. So I think I'm in the right range if I say 2 to 4 kilobytes. It should be something like a little over a dozen, let's say about 15 group elements. So someone could do the math and see how many kilobytes that works out to. I'll probably mess it up if I try to do it on the fly. Should be something like 15 times, I don't know, 40 bytes. 40. Yeah, I guess that's looking like more like 1 kilobyte. So I'm off by a factor of 2 or something somewhere. So either I'm underestimating the size of a BLS like 12381 group element, or I'm underestimating the number of group elements in the proof in Marlin. But anyway, so nice small proofs. So that's the big benefit. So the cons are twofold. So in order to get this nice small proof size in Marlin, Marlin has to use KZG commitments, which we'll discuss what these are in some future, probably in the couple months would be my guess. And so this is a certain very popular polynomial commitment scheme. It's particularly popular because the commitments are really small and the evaluation proofs are really small. But it does require a trusted setup, as well as a pairing friendly group, which somewhat limits the group one works over, and increases certain costs because the group elements are a little bit bigger than groups that aren't necessarily pairing friendly. So in comparison, Spartan can be transparent and not need pairings. So whether or not it needs a pairing friendly group, or whether or not it's transparent, depends entirely on just the choice of polynomial commitment scheme. And the same goes for Marlin as well. Like you could swap out KZG commitments in Marlin for something like bulletproofs, or something transparent. But then you'd be giving up on essentially the most important benefit of Marlin relative to Spartan, which is smaller proofs. And the point here is that because Spartan uses the sum check protocol, the proof size, no matter what polynomial commitment scheme you use, will always consist of at least log n field elements, where n is like the size of the R1CS instance, as well as if you're applying fiat Shamir to make sure the protocol is non-interactive so that you get a snark, the verifier is also going to do logarithmically many hash evaluations. And so, and then Spartan also requires one evaluation proof, or let me say one commitment and one evaluation proof from whatever polynomial commitment scheme it chooses to use. And the yeah, so no matter what polynomial commitment scheme you choose to use, there's always like a log size proof. You just can't get the proof shorter than log size unless you start using snark composition or recursion. Whereas in Marlin, because it avoids the sum check protocol, it's actually we'll see today the way Marlin's designed. It's actually an interactive protocol with constantly many rounds that you then apply fiat Shamir to. Because it has constantly many rounds. In fact, the number of rounds is something like just two rounds or something like that. I think it's 2 rounds. The prover commits to several polynomials in each round. Okay. So and each commitment is like another group element. So you wind up that's why you wind up with like 15 or more group elements in the proof. But because it's only constantly many rounds, and constantly many polynomials being committed to in each round, ultimately in Marlin the proof size is constantly many group elements, which is shorter proofs than I think what comes out of the sum check protocol in Spartan. Yeah, so like in Spartan, there's kind of no point to ever try to use a polynomial commitment scheme that has like shorter proofs than the proof size in the sum check protocol, because then you're sort of optimizing a low order contribution to the proof size if you even had such a polynomial commitment scheme available. Whereas in Marlin, because it's constantly many rounds instead of logarithmically many rounds before fiat Shamir is applied, if you use a polynomial commitment scheme like KZG with like tiny evaluation proofs, you wind up in the end with kind of a constant size proof. Okay, so yeah, that is one con of Marlin is the trusted setup and the pairings, and the other con is just a slower prover. And basically, this happens because the prover just commits to many more polynomials than in Spartan. And this will, why that is the case will become very clear as we discuss how Marlin works today. So it's basically just like a direct tension between verifier costs and prover costs, where Marlin has better verifier costs but worse prover costs. Okay, so that's the comparison, and that's why we didn't just like stop the reading group when we covered Spartan. There's other trade-offs to be had by looking at different techniques. But we'll see that there's nonetheless a lot of similarities between what's happening in Marlin and what's happening in Spartan. Okay, so that's what we're going to talk about today. Let me pause here and see if anyone wants to ask any questions.
Is Spartan and Marlin the only two IOPs for R1CS?
For R1CS, IOPs, I'd say the only other snark for R1CS that you really need to know would be at least without going into recursion, like Nova can prove statements about like iterated R1CS or something like that, but let's ignore that. So Growth 16 supports R1CS, but it's not quite a polynomial IOP. Yeah, it doesn't quite go through the polynomial IOP plus polynomial commitment paradigm. But it's not far off that. But it is not exactly the same. And one way to see that it's not exactly the same is Gross 16 does not use fiat Shamir. And anything that goes through this polynomial IOP paradigm does wind up using fiat Shamir. But yeah, so Gross 16 does nonetheless use something cryptographic techniques that look a lot like KZG commitments, and it uses something that is its information theoretic component is it's not a polynomial IOP, but it's something very similar, like a linear PCP or something like that. So anyway, yeah, the other snarks that are popular are Planck and Starks. Now, Planck does not support R1CS without overheads. And this is actually, my view of this is probably controversial, but I'll nonetheless share my view with you. So now that, sort of my recent paper has made clear that like Spartan and Marlin, which were originally described for R1CS, can prove statements about the other circuits people like to use today, namely Planckish and Air, and in fact can prove statements about a generalization of all of these that we're calling CCS. This means that the community's view of Spartan and Marlin as like they were viewed as supporting like less general kinds of circuits because people didn't think they could support Planckish and Air, and that's what people seem to want to use rather than R1CS. And in fact, the opposite is true. They can support Planckish and Air, and they also support R1CS, whereas Planck does not support R1CS. And then with Starks, Starks support Air. They do not support R1CS. If you look at the paper Fractal, roughly speaking, like the point of Fractal is to like adapt like the Stark like techniques to R1CS. And really what it did was it took Marlin, which works for R1CS, and just replaced KZG commitments with Fry. And then did some optimizations to like specific to the fact that now you're using Fry, and so you can like do certain things that are make sense to do if you're using Fry, but don't make sense to do if you're using KZG commitments. So in some sense, like you can make Starks work with R1CS, but the way you would do it is you would take Marlin and just like switch out the polynomial commitment scheme. And also I'll add like, again, opinion, I suppose, but once you're using Fry and Marlin, like you're giving up on the short proofs. And so I don't see the point of this. Like at that point, you should be using something like Spartan. You should be using the sum check protocol to minimize the prover's commitment cost. So call this a personal opinion, but I think like the Spartan prover is significantly faster than the Fractal prover for this reason. So should use the sum check protocol instead to minimize provers costs. Once you decide to use Fry, which is going to give you pretty big proofs, there's really no point to using the techniques in Marlin. The whole point of these techniques kind of relative to the sum check protocol is to have something that's constant rounds to keep the proofs shorter. If you are using something like KZG as your poly commit, which has short proofs, if you use Fry, you don't have short proofs from the poly commit. So what was the point of kind of paying a price to get the number of rounds to be constant? Did that make sense? Was that a reasonable answer?
Yeah, yes, thank you.
Cool. Other questions? All right. Okay, so if there are no other questions, we'll dive into how Marlin works. So let me remind you what problem the sum check protocol solved, and what we're going to see is that Marlin is just like an adaptation of the techniques we already sort of saw in Spartan, like the sum check protocol and stuff. It's just we're going to take each like piece of the protocol and sort of adapt it to use univariate polynomials rather than multivariate ones. So the sum check protocol takes a multivariate, let's say L variate polynomial G, and the goal is to compute the sum of G's evaluations over the Boolean hypercube. All right, that's the sum check protocol that we spent a lot of time on over the preceding couple of months. And Marlin wants to study a univariate version of this. So it says consider a univariate polynomial Q. Let me call it Q of degree at most n. Okay, and its goal is to sum up evaluations of Q, where now the sum is over a set capital H. Because Q is univariate, this set has to be like a subset of the fields that Q is defined over. So let me tell you what this set is. In practice anyway, H will be the nth roots of unity in the field. So that is all x in the field such that x to the n minus 1 equals 0. Okay. So that is the problem that is sort of at the core of Marlin, in the same way that this problem of summing up some multivariate polynomials evaluations over the hypercube is at the core of Spartan. And so these nth roots of unity are some kind of like univariate or one-dimensional analog of the Boolean hypercube. There's certain ways you can make that formal. So Marlin relies on a fact that characterizes this sum. So it wants to give like a clean expression for this sum. It will then use that expression to give an efficient protocol enabling a prover to prove what this sum is. Okay, so here's the fact. Let me just make sure I write this down correctly. One second. The fact is, remember, for any univariate polynomial Q of degree at most n, let's say strictly less than n, this summing up Q's evaluations over the nth roots of unity is equal to n times Q of 0. Okay. Let me just pause and see if anyone wants to ask any questions about this statement before I'm going to be very sketchy as to the proof. There's like a very careful proof written out in the book, and I'm just going to kind of give a sketchy summary of how that proof goes, how to think about it. But does the statement make sense? Does anyone want to ask any questions? Okay. All right. So I think let's suppose Q of x is let's say C0 plus C1 times x plus C2 times x squared up to Cn minus 1 times x to the n minus 1. Okay. Let's focus on C1 times x. Okay. So what when we sum up So we're interested in summing up Q's evaluations. Sorry, I wrote this wrong. I should have written Q of X rather than Q's. So we're summing up Q's evaluations over the nth root to unity. That is, the problem we're interested in. So when we sum up, these values, Q of X, we can just break this sum into terms, like one monomial at a time, right? So it's like sum over, X and H, like C0 plus sum over X and H C1 times X plus, so all I'm doing is sort of distributing the sum across like each term of in the definition of Q, Cn minus 1, X to the n minus 1. And these are, lowercase x's we're summing over. Cool. So, and I'm just focusing now just on this sum. So, this sum is C1 times sum over the nth root to unity of just that, the nth root of unity. So I want to talk about what is the sum of all nth root to unity. Okay. And whenever you think about nth root to unity in the finite field, I find it helps to just pretend like we're talking about the nth root to unity over the complex numbers, even though we're not. But they behave very similarly. So let me just sort of give you a brief review or just overview of the nth root to unity as complex numbers. So if we're talking about n equals 2, the two root two root to unity would be 1 and minus 1, right? Because these are the unique complex numbers that when you square them you get out 1. Okay, now if I talk about the fourth root to unity, so the complex numbers that if you raise them to the fourth power you get out 1, you would still have 1 and minus 1, but you would also have I and minus I. Okay. And now you can check, like, if you add up the fourth root to unity, well 1 plus minus 1 is 0, and so it, like, I plus minus I is also 0. Okay. So you can kind of pair up the fourth root to unity and such that they cancel out with each other, and therefore their sum is 0. And the same thing would happen if we looked at, like, the eighth root to unity. Then we would have, if I'm drawing the eighth root to unity as, in the complex, amongst the complex numbers, there would be 8 of them rather than 4, and the additional 4 that weren't already there would kind of be, halfway as you, move around the complex unit disk, between each of the fourth root to unity, and you can, just check that, like, for each eighth root of unity, its negative is also there. And this really just because we're talking about, like, even powers, right? So if you take some eighth root of unity, it's the negative of that is also an eighth root of unity, just because -1 to the eighth power is 1. And so what I have sort of rambled an explanation of for you is that summing up the nth root to unity is going to give you 0. Okay, and basically it turns out that, like, this sum would also be 0 even if we were summing up not the root to unity itself, but their squares or their cubes or their fourth powers and so on and so forth. So I think I'll just leave it at that. So basically, every term of the sum, like, is just is nothing, sums to 0, except for the very first term. And here we're summing up a constant. That constant is exactly Q of 0. It's the constant term of Q, which is Q is 0, and we're summing it up n times. And so that's what I've written here, n times Q is 0. Okay, so that's the fact. Okay, does anyone want to ask a question about that? No? Okay. So with that fact in hand, I can state one, like, other fact that's, like, on an almost immediate corollary of the first fact, And this fact is what's going to underlie what Marlin calls the univariate sum check protocol. Yeah, this corollary is that summing up, well, here I guess we're going to talk about. Okay, so let P be a univariate polynomial of degree D, where D could be any degree. Then we're interested in summing P's evaluations over the nth roots of unity. And let's say understanding when that sum is exactly 0. And that holds if and only if there exists two polynomials. The book calls them H star and F. I don't think it really matters, but let me tell you what the degree of these things are. The degree of H star is at most D minus N, and the degree of F is at most, well, the book says less than N minus 1, but I feel like it's probably less than or equal to N minus 1. So that I have to remind myself that there's a typo there, I think. So we'll find out if there's a typo or not. Such that P of X equals H star times X to the N minus 1 plus X times F of X. Okay, now here's what's happening here. So this X to the N minus 1, this is called the vanishing polynomial for the nth roots of unity. So this is the polynomial that maps all nth roots of unity to 0 and doesn't map anything else in the field to 0. This is often denoted bold Z sub H to indicate that it's the polynomial, the unique polynomial that kills all elements of H and doesn't kill anything else. And by kill, I mean maps to 0. And so what's happening here is the way to obtain H star and F from P is to just divide. So here's like a little sketch of the proof. Like what we'll do is we'll divide P by this vanishing polynomial Z sub H. And that will give us a quotient. So let H star be the quotient. And let's say R is the remainder. Okay, so that means P equals H star times the vanishing polynomial plus R. And we know, we're guaranteed that the degree of R is at most, I guess it's N minus 1, which means the book doesn't actually have a typo. Sorry, it does not have a typo. And yeah, because by definition, this vanishing polynomial vanishes on H, okay, that means if I am interested in summing up P's evaluations over the nth roots of unity, like this term contributes nothing to the sum, right? Because for any nth root of unity A, when I feed A through Z sub H, it equals 0. And so H star of A times 0 is 0. So that means that summing up P's evaluations over the nth root of unity is the same as summing up R's evaluations over the nth roots of unity. And we saw from the earlier fact that that sum is 0 if and only if the R of 0 is 0. Right, because the fact before said that this sum was R of 0 times N. So that's going to be 0 if and only if R of 0 is 0. And then R of 0 being 0 is equivalent to R being writable as X times some F of X of degree at most N minus 1, because N minus 1 is the degree of R, and we're getting degree 1 from this X term. So the point is, R0 being 0 means the constant term of R is 0, which means X divides every term of R, right? Because X divides every monomial except for like a constant term. X divides X divides X squared, X divides X cubed, right? So if there is no constant term, then X divides every monomial in R. That means we can write R as X times f of X. Yeah, so that's the proof of like kind of the non-trivial direction of this fact. Okay, so just to sum up, if the verifier in Marlin is interested in summing up all evaluations of some univariate polynomial over the nth roots of unity, like that sum is 0 if and only if we can identify this, this H star in F so that we can express the polynomial being summed as H star times this vanishing polynomial plus X times f of X. Okay. And so that brings us to the univariate sum check protocol. Okay, and I want to, so the problem solved by this protocol is the univariate analog of the sum check protocol we're used to. Namely, the goal is, like the prover claims that the sum over all nth roots of unity of P of A is 0, for some univariate polynomial P. And yeah, some univariate P. So that problem is the univariate analog of the problem considered by the standard sum check protocol. But mechanistically, the univariate sum check protocol is nothing at all like the standard sum check protocol, because yeah. So the way the prover is going to prove this is by sending two pretty big polynomials to the verifier. And so in practice, you wouldn't want to actually send those polynomials to the verifier. You'd have the prover like commit to them with the polynomial commitment scheme, and the verifier in the protocol is going to need to evaluate each of the committed polynomials at a random point. And so it'll get the evaluation like via, the evaluation, procedure of the polynomial commitment scheme. So whereas the multivariate, like the standard sum check protocol, which I now sometimes call the multivariate one, sort of this terminology sort of forces that upon us for clarity. So we, which of the, whether we're talking about univariate or standard sum check. In standard sum check, there's no cryptography, right? The prover, the goal is to sum up all evaluations of some multivariate polynomial over the hypercube, and there's one round per variable, and the prover sends a low degree univariate polynomial in each round, and so the prover just sends those messages like in full. Whereas in the univariate sum check protocol, as we're about to see, the prover winds up cryptographically committing to these polynomial. There's only like one round, and the prover is committing to the polynomials. So there's cryptography in there kind of from the gun. Yeah, so mechanistically, they're very different. So the way the prover in the univariate sum check proves that this sum is 0 is it just sends, in practice, it would be commitments to, but let's just say sends H star and F to the verifier, and claiming that P equals H star times the vanishing polynomial x to the n minus 1 plus x times f of x. Okay, now the verifier needs to check that this equality holds. And the way it's going to do that is by it picks it's just going to, so the prover's claiming, hey, like P of x as a polynomial equals this other polynomial. And the verifier is going to just evaluate the left-hand side and the right-hand side at a random point and confirm that the left-hand side and the right-hand side agree at that random point, right? And the point is, if the left-hand side and the right-hand side are not the same polynomial, then the probability that they agree at a randomly chosen point is at most their degree over the size of the field. So as long as the field is much bigger than the degree of anything, on the left-hand side or the right-hand side here, then kind of checking that this equality holds at a random point is kind of enough, is equivalent up to small soundness error to confirming that the equality holds actually as formal polynomials. So the verifier picks an R from the field at random, confirms that P of R equals H star of R times R to the n minus 1 plus R times F of R. Okay, and if this holds, then the verifier believes that the prover's claim is true, and hence that the evaluations of P over the nth roots of unity indeed sum to 0. Okay, so in Marlin, when this gets applied, like P will already be committed, like before the univariate sum check protocol even starts, and then the prover commits to H star and F during the univariate sum check protocol. And so each of these three evaluations are going to come from the polynomial commitment scheme, more or less. And there's going to be some details about exactly how P is specified. So right now, let's just imagine that P was committed. And so the verifier can just go to the commitment scheme and say, hey, tell me what P, the committed polynomial is at R. And again, it'll be a little more complicated than that, but not much so. So that is the univariate sum check protocol. Yeah, so it's basically it's sort of one round of interaction because the prover sends these polynomials like H star and F. The verifier responds with R, and the prover reveals H star of R and F of R. And that's since this is kind of the core of the Marlin protocol, this is sort of why Marlin is constantly many rounds, whereas standard sum check would be logarithmically many rounds. Okay, so that is univariate sum check. So now I need to explain how to use univariate sum check to give a snark for R1CS. But let me pause here, see if anyone wants to ask any questions. No, everything's good? Okay, somebody want to confirm? Okay, I heard a question, so that's great. What's up?
No, that's not for a question. It's for just to say everything's good.
Okay, awesome. Yeah, thanks for confirming. Okay, so yeah, remember with R1CS, there are three public matrices, A, B, and C. That means both the prover and verifier know these matrices, and the prover claims to know a Z such that AZ Hadamard product BZ equals CZ. Okay, and as a reminder, Hadamard product is like entry-wise product. So let's say there are m rows and n columns in these matrices. So each row is like a constraint. And so the ith constraint is of the form like the ith entry of AZ times the ith entry of BZ equals the ith entry of CZ. So for all I equals 1 to m. Okay, that's R1CS. And there are some annoying details I'm ignoring now, like if as written, the all zeros vector Z is like always a solution to this constraint system. So what in practice, like really what's happens is we sort of fix the like the first entry of Z to be 1 and stuff like that. And that ensures that this problem is actually NP complete. And indeed, you can like take any computer program and that takes as input a witness and confirms that the witness satisfies the property that the prover claims it does, and turn it into an equivalent R1CS instance where the size of the R1CS instance is not actually that much bigger than the runtime of the computer program. And for simplicity, let's just take m equals n. So the number of constraints and the length of the vector Z are the same. That's just going to make notation easier for the rest of the presentation. Great. So let's see. I guess at the start of Marlin, the prover sends to the verifier. Now, Okay, so I'm going to start by imagining the prover sends very long vectors to the verifier, and then what the prover is actually going to send is commitments to the univariate low degree extension of these vectors. Okay, but like before I start talking about univariate low degree extensions, let me just tell you what the vectors are. So let's say the following. It'll send the witness vector Z. That is the solution that it claims to know to the R1CS. It'll also send AZ, BZ, and CZ, but let me call that ZA, Z sub A. That's just shorthand for A times Z. Z sub B, that's just shorthand for B times Z. And Z sub C, that's just shorthand for C times Z. Okay. Now, as I babbled a moment ago, it doesn't actually send these giant vectors. These are each of length n. Really, Z is of length n, and ZA, ZB, ZC are of length m. But we're assuming that m and n are the same just for simplicity. At any rate, these vectors are too big. Like, we don't actually want the prover to have to send these whole vectors to the verifier. Okay, so what we're going to do is we're going to take what's called the univariate low degree extension of these vectors, and I'm going to denote those by sticking a hat over each of these vectors. And this is just like the univariate analog of multilinear extensions. But let me explain in a little more detail. Okay, because the univariate sum check protocol is phrased as summing up evaluations of a univariate polynomial over the nth root to unity. Okay, we're going to need to index. So I'm trying to tell you, what are these univariate low degree extension polynomials? So, like, how do you go from Z, which is a length n vector, Z1 up to Zn? How do you go from Z to the polynomial Z hat? Okay, and the answer is I'm going to index entries of Z by the nth root to unity. Okay, so let me denote their n nth root to unity in the field. Let me denote them by A1 up to AN. So these are each an nth root to unity. Okay, and what we're going to require is that we're going to define Z hat via univariate Lagrange interpolation, and I'll give you a quick reminder in a moment what that is. But define via Lagrange interpolation. So Z hat maps any nth root of unity to the associated entry of Z. Okay, so that is we are just interpreting Z as the list of all evaluations of Z hat over an interpolating set. And that interpolating set being the nth root to unity. So this is the interpolating set. And this is completely analogous to how we define multilinear extensions. In the case of taking the multilinear extension of a vector like Z, which I denoted Z twiddle, Z twiddle interpreted the n entries of Z as the evaluations of Z twiddle over the Boolean hypercube, over 0, 1 to the log n as the interpolating set. Now the interpolating set is not the Boolean hypercube, but it's the nth root to unity. And so, it's the natural, like low degree extension that has the nth root to unity as its interpolating set is univariate. And yeah, if it would help for me to give an explicit expression for Z hat, it's the following. So you take the first entry of Z1 of Z, so Z1, and you multiply it by the Lagrange basis polynomial that pulls out that kind of picks out the first nth root of unity. So let me call that, I don't know, delta A sub 1 of X. And this is just defined to be the unique degree n-1 polynomial such that delta a sub 1 of a sub 1 is 1 and delta a sub 1 of h equals 0 for all other nth root to unity h and h. And so, when you that ensures that when you evaluate z hat at a1, you get z1 times 1, which is z1. And this term will not affect the evaluation of any other nth root of unity because when you evaluate delta sub a1 at any other nth root of unity, it spits out 0. Right. And then the second term would be z2 times delta sub a2 of x. This would make sure that a2, the nth root of unity a2 maps to z2 and doesn't affect the evaluation of z hat at any other nth root of unity, and then there's z3 times delta a3 and so forth, zn times delta an. So that's z hat. And similarly, z a hat, z b hat, and z hat do the same thing. So they interpret az, bz, and zz. These are length n vectors as like the desired evaluations of a univariate polynomial with the interpolating set being the nth root to unity. Okay, any questions about that? Okay, so the prover at the start of Marlin actually sends, KZG commitments. And again, it doesn't matter how KZG works. We'll talk about that later. Not today, later in like a couple months or something. To z hat, za hat, zb hat, and zc hat. Something I should mention here is that KZG commitments require the prover to know the coefficients of the committed polynomials in the standard monomial basis. And that is the prover does not know those coefficients at the start. It only knows the coefficients in what I call the Lagrange basis. So z1, z2 up to zn are the coefficients of z hat in the Lagrange basis. Where this is like the first Lagrange basis polynomial and this is the nth. But KZG commitments, the SRS is like powers of tau, and that requires the prover to know the coefficients. If you write z hat as like c0 plus c1 times x plus c2 times x squared, that's what I mean by the standard monomial basis, and that's what the prover needs to know to apply KZG commitment scheme. So that's what the prover is going to have to do is compute a change of basis to obtain the coefficients of z hat and za hat and zb hat and zc hat in the standard monomial basis, and that requires an FFT, really, I guess 4 FFTs of length n, which is can be expensive, especially for large circuits. So yeah, snarks like Marlin and Planck, like, the prover in my view is quite expensive for them. And the expense is kind of coming from multiple places. One is just KZG is applied to commit to a whole bunch of different polynomials, and that's just a lot of group work. KZG commitments require the prover to do multi-exponentiations in a group, but also the prover has to do FFTs just to get the coefficients of the polynomial that it wants to apply KZG to. And we'll see the prover is going to wind up committing even to more polynomials other than these because of the way the univariate sum-check protocol works. Okay, but anyway, so that's how the protocol begins, is the prover sends commitments to these 4 polynomials, and now the verifier needs to check, let's say 2 things. Okay, so let me kind of present them backwards. So the second thing it will check, because it's a little harder to check than the first thing, so that's why I'm numbering it number 2 by presenting it first. The second thing it will need to check is that ZA hat indeed extends AZ, A times Z. ZB hat indeed extends B times Z, and ZC hat indeed extends C times Z. So that is, it needs to check that ZA hat, ZB hat, and ZZ hat are what they're supposed to be. They're supposed to be the univariate low degree extension of these three vectors. So the verifier can't just trust that that's the case. It's going to have to check it. And then the other thing the verifier needs to check is assuming ZA hat, ZB hat, and ZC hat are what they're supposed to be. It's going to use them to check that Z satisfies the constraints. So that is AZ Hadamard product BZ minus ZZ equals 0. And another way to check that, to express that, is to say that for all nth root to unity H, ZA hat of H times ZB hat of H minus ZC hat of H equals 0. So that's just another way of writing out these constraints. Yeah. Okay, so does it make sense that if the verifier were able to check these two things, it would be convinced that indeed Z satisfies the R1CS instance? Cool. Okay, so let's describe first how it's going to check that 1 holds. This is pretty straightforward. So now we saw a statement like this in Spartan, right? In Spartan, the prover like committed to the multilinear extension of the witness, and then checked that some derived polynomial like G sub Z, like G of X, which what it actually was something like add twiddle of ABC. Here X was like ABC. The details don't matter. It was like Z twiddle of A minus Z twiddle of B plus Z twiddle of C. Yeah, the details don't really matter, but it had to check that something vanished over the Boolean hypercube. So it needed to check that G of ABC equaled 0 for all ABC in the Boolean hypercube. And this is just a univariate analog of that. Where now we're checking that this thing that I just drew a box around, I'll draw it in blue, now needs to check that the left-hand side here vanishes over not the Boolean hypercube, but the univariate analog of the Boolean hypercube, that is the nth root to unity. Okay, and in how does the verifier check that? This left-hand side here vanishing over the nth root to unity is equivalent. So suffice it, it's equivalent to check that the vanishing polynomial of the nth root to unity, remember that's x to the n minus 1, divides the left-hand side here, what I circled in blue. So divide ZA hat times ZB hat minus ZC hat. Okay, right, because so this is like an easy fact to see in both directions. Like obviously if the vanishing polynomial divides something, that is if you can write that something so that's something ZA hat times ZB hat minus ZC hat, if you can write that as a product of something times the vanishing polynomial, well the right-hand side clearly evaluates to 0 for all x in the set capital H, and so that means the left-hand side also has to equal 0 for all x in the set capital H. So clearly, if the vanishing polynomial divides this thing, then the thing vanishes over the Boolean hypercube. You can also show that if this thing vanishes over the Boolean hypercube, then the vanishing polynomial divides it. And you can kind of show that just by like factoring out the roots. The details aren't important. You should just believe me and think about it a little offline if it's not obvious to you. Okay, so that means in order to prove that what I called 1 before holds, that is that this thing here vanishes over the nth root to unity, the prover just sends the quotient polynomial. Okay, and then the verifier, checks it as usual by picking a random point and confirming that ZA hat at that point times ZB hat at that point minus ZZ hat at that point equals the quotient polynomial times the vanishing polynomial at that point. So, if the left-hand side and the right-hand side agree at a randomly chosen point, as long as the field is much bigger than the degree of any of the polynomials, appearing on the left-hand side or right-hand side, it's safe for the verifier to believe that the left-hand side and right-hand side are actually the same polynomial. And so that it's safe for the verifier to believe that the vanishing polynomial indeed divides this thing, and hence that this thing vanishes over the Boolean hypercube. So that is how this first thing, 1 here, is checked. So we're done. We're done checking that. Okay, so what's left is to check number 2 here. That ZA hat indeed extends A times Z, ZB hat indeed extends B times C, and ZC hat indeed extends C times Z. So I'm just going to explain it for A because it's completely the same procedure for B and C. So let's talk about that. So how does V check that ZA hat of H equals the hth entry of AZ for all H in capital H? Okay. So here's how we do it. I'm going to give a simple expression for like the true extension polynomial of AZ. Okay. So yeah, so let me give that a name. The true the true degree n-1 extension of AZ. So let me give that let me call that maybe I'll call it S. So let S of X be the unique degree n-1 polynomial, such that S of little h equals A times Z hth entry for all nth root to unity little h. So I'm going to give it a convenient expression for S of X. Now, that expression is going to involve interpreting or taking a bivariate extension polynomial of the matrix A. Okay, so let A hat of X comma Y be the unique bivariate polynomial of degree at most n, or I guess it's n-1 in each variable, such that A hat of H comma H prime equals A of H comma H prime for all H and H prime in the nth root to unity. Okay, and just a quick example, say A is, I'm just going to do a 2x2 matrix so that it's nice and small and I can work it all out. Let's say A is 1, 3, 2, 6. Okay, and then so we'd be using second root to unity. Remember, the second root to unity in a finite field as over the complex numbers are just -1 and +1. So I'll label like the first column as -1 and the second column as +1. The first row as -1 and the second row as +1. So A hat of XY, I'm just going to give an expression for it via Lagrange interpolation. It would be 1 times, so I need to write down the Lagrange basis polynomial that sort of maps -1 to 1, and any other combination of -1 and +1 to 0. So I think that would be x plus 1 over 2 times y plus 1 over 2, right? So this maps, x plus 1 over 2 maps -1 to 1, and no, I did it backwards. Sorry. I think it's x minus 1 and y minus 1 over 2. It's 1 minus x. Sorry. It's 1 minus x and 1 minus y. Yeah, that's it. So that maps, so you can check this maps -1 gets mapped to a 1 and 1 gets mapped to 0. So this product here maps -1 to 1, and any other combination of -1 1 1 minus 1 or 1 1 to 0. So that's the first term in the Lagrange interpolation expression for a hat. The second would be 3 times I guess it's 1 minus x over 2 times 1 plus x over 2. And that ensures that -1 comma 1 maps to 3, if I'm doing things right. Yeah, I think so. And then the next one would be 2 times 1 plus x over 2 times 1. That should have been a y. 1 minus y over 2. And then finally, we have 6 times 1 plus x over 2, 1 plus y over 2. Okay, so that's what I mean by the bilinear low degree extension polynomial of A. Okay, any questions about this? So this is completely analogous to, how Spartan took A and looked at its multilinear extension polynomial. This would have been if there are n rows and n columns, this would have been like a 2 log n variate polynomial of degree n plus 1 in each variable. This thing, a hat, is not 2 log n variate, it's 2 variate, it's bivariate. And its degree in each variable is not 1, its degree is up to n minus 1 in each variable. Okay, so we've just, this is exactly what we've done before. The only difference now is there are 2 variables rather than 2 log n variables. And accordingly, the degree in each variable is much larger. And we're indexing things, rows and columns, not by 0, 1 to the log n, but rather by nth roots of unity. Okay. Any questions?
I do have one question.
Yeah, please.
For the prover, what is the step that makes it the more cumbersome to calculate? Like, is it to calculate the quotient of the that divides the polynomial?
I'm sorry. The question was, what is the bottleneck for the prover?
Yeah. What is the step that makes it longer or shorter in terms of time and calculation?
Yeah, so I'd say the big thing in Marlin that makes the prover take a lot of time, especially like relative to something like Spartan. I mean, it's really 2 things. It's the prover is committing to many different polynomials, whereas in Spartan, especially if there's repeated structure in the constraint system, the prover only will commit to the witness vector itself, z. So it doesn't have to commit to all these quotient polynomials, doesn't have to commit to, ZA hat, ZB hat, or ZC hat. And then the other thing that could be a bottleneck is the prover needing, when it does commit to these things, it needs to know the coefficients of the polynomial to be committed in the standard monomial basis, which requires an FFT. And so one of those things should be the bottleneck. So either the work of like computing the commitments once you know those coefficients, or just computing the coefficients themselves could potentially also be a bottleneck. This bivariate polynomial thing, like the fact that it's using like bivariate instead of multilinear is like not inherently a bottleneck. But for the issue that, by going the reason it's using bivariate things is so that it ultimately obtains like a constant round protocol. But the reason it's able to obtain a constant round protocol is because the prover is committing to all these quotient polynomials and things. So it's all kind of intermingled. Like what if you ask, like, I can tell you what the operations are that are the bottleneck, but if you ask me like where is that bottleneck kind of conceptually coming from, everything's kind of intermingled. Like it's just if you're going to use if you want a constant round protocol, I think the only way we know how to do that really is to use univariate polynomials and have the prover like send these quotients. And that unfortunately requires extra commitments from the prover and so forth. Was that a clear enough answer?
Yeah, totally. Thank you.
Yeah, thanks for the question. Other questions? Cool. Okay, let me. Oh, question.
So just one small question. So the prover doesn't need to commit to the quotient polynomial, like the vanishing polynomial, right?
Right, because the verifier only ever needs to evaluate that vanishing polynomial at like a random point or maybe two random points, and it can do that on its own in logarithmic time. And this is really like the main reason to use, like, the reason we use the nth roots of unity as the interpolating set is so that like they are specific. Nth roots of unity are like basically defined so that their vanishing polynomial is sparse. So its vanishing polynomial only has two terms, only two monomials, x to the n minus 1. So to evaluate this at a random point is just r to the n minus 1, and this can be computed in with log n field operations. So yeah, there's no need for the prover to commit to that polynomial. The whole point of the prover committing to things is so that the verifier can later say, hey, I need to evaluate the committed polynomial at a point. And in this case, the verifier can just do that evaluation on its own.
But so wouldn't this make the verifier logarithmic instead of constant time?
Yeah, so it does. So good point. It's so firstly, it doesn't affect the proof size. But it's just verifier time. And then secondly, logarithmically many field operations is actually going to be much cheaper than the pairing operations that the verifier needs to do to verify KZG commitment evaluation proofs. So, like, concretely and even asymptotically, I think like a pairing operation is more expensive. I think even asymptotically than log n field operations. Certainly concretely. So it doesn't really matter.
Oh, so it's constant in the number of pairing checks.
Yeah, the verifier, the like the Marlin verifier and the Planck verifier, they compute a constant number of pairings. It's probably somewhere between 2 and, yeah, I don't know offhand, somewhere between let's say 2 and 5. I don't know how many exactly. And those are almost certainly the bottleneck for the verifier. Definitely more expensive than computing R to the n. If there's a public input to the R1CS instance that's really big, the verifier does have to do like a multi-exponentiation of size equal to the length of that public input. And so if it's like a really big public input, that would actually be even more expensive than the pairings. And people, I think people always say the pairings are the bottleneck. So I think this situation is just like if you actually had a really big public input to the R1CS instance, you'd wind up doing what's called the hashing trick, and you'd feed into the R1CS instance not the full public input, but just a hash of it, and then the prover would prove it knows a pre-image of the hash, kind of as part of the statement, and that way it avoids the verifier having to do a very big multi-exponentiation as part of its verification procedure. Anyway, that's a long rambling way of saying the bottleneck for the verifier should be like something like 2 or a handful of additional pairing operations.
Yeah, makes sense. Thank you.
Yeah, thanks for the question. Other questions? Cool. All right. So coming back to this final check that the verifier needs to do. Okay. So yeah, I defined this bivariate extension of the matrix A. Let me erase everything from the example. All right. So remember, what the verifier is trying to check here is basically that ZA hat, which is the committed polynomial, equals S. S is what ZA hat is supposed to be. So S is the low degree extension of A times Z. Okay, so I'm going to give a nice expression for S. So here it is. So S of X is the sum over all J, nth root to unity J, of A hat X comma J times Z hat of J. Okay, so let me call this like a claim. And we've seen claims like this before. Just typically we were dealing with multilinear things, not univariate things. So in order to check this claim, we have to check two things. Remember, S is defined to be the unique polynomial of degree at most n minus 1 with this pointwise behavior, that is S of H equals A times Z eighth entry for all nth root to unity little h. So we need to check that this right-hand side to prove the claim. We have to check that the right-hand side has degree at most n minus 1. And we have to check that if you evaluate it at little h, it spits out A times Z hth entry. Okay, and both of these, if both of these things hold, then this, the right-hand side is the unique polynomial of degree at most n minus 1 with this pointwise behavior, and that polynomial is unique, and S was defined to be the unique polynomial of that degree with that behavior, so they must be the same polynomial. Okay, so let's check these two things. The degree bound is obvious because A hat was defined to have degree at most n minus 1, and X is only fed into A hat. So clearly this is a degree n minus 1 polynomial in X, right? So like, if you ignore this sum so that J becomes a variable, this thing actually has degree 2n, up to 2n or 2n minus 1 or whatever in J, but then that high degreeness gets summed away. And what's left is a degree n minus 1 polynomial in X. And that's so yeah. So the right-hand side does indeed have degree at most n minus 1 in X. And then the second thing, checking that if you evaluate the right-hand side at any nth root to unity little h, it spits out the hth entry of A times Z. Well, that's just the definition of matrix vector multiplication, right? That's just the fact that A times Z hth entry is the sum over all columns J of A H comma J times ZJ. That's this thing is the same as this thing, just because A hat and Z hat are defined to be extension polynomials of A and Z, respectively. And I'm doing some funky indexing here where, like, here I've indexed the rows by nth roots of unity, and here I've indexed the columns and the entries of Z by numbers between 1 and n. But you should hopefully be getting a little bit comfortable where we just kind of, index things by whatever is convenience for whatever reasoning we're doing at the time. Okay, great. So we've got this convenient expression for what ZA hat is supposed to be. And as usual, the verifier is just going to check the expression holds by confirming it holds at a random point. So that is, so the verifier, needs to check by the reasoning above that that ZA hat of X equals, this right-hand side here, sum over J, A hat of X comma J times Z hat J. And so what it's going to do is it's going to pick a random R from the field and confirm that just check the equality at R. So confirm that ZA hat of R equals sum over J in the nth root to unity, A hat R comma J times Z hat J. Okay, so, and the cool thing now is, the verifier will get ZA hat of R. Remember ZA hat was committed. So ZA hat of R can be obtained, just from the polynomial commitment scheme used to commit to ZA hat. So the remaining question is, how does it obtain this sum? And that is finally where we invoke the univariate sum check protocol. Okay, so let's let G of J be defined to be A hat of R comma J times Z hat J. Maybe it'd be helpful if I call this X instead of J, just so it's clear it's a variable. And the prover is at this point claiming that if I sum up G's evaluations over the nth root to unity, I get out ZA hat of R. Okay, and remember, the univariate sum check protocol was exactly constructed to prove that a sum of this form is zero. Okay, so we do have the one little nuisance that the right-hand side here is probably not zero. It's whatever ZA hat evaluated to at R. So what we're going to do, we're going to apply the univariate sum check protocol not to G itself, but just to little tweak of G, which is just specifically designed so that, if this equality holds, then the thing we do wind up summing equals zero. So that is, we apply univariate sum check not to G itself, but to G of X minus ZA hat of R times N inverse. And that's just, we're doing this because if I call this, I don't know, let me call this just Q. So sum over all nth root to unity of Q equals zero if and only if sum over all nth root to unity of G is QA ZA hat of R. So I just define this term specifically so that, when I sum it all up over the nth root to unity, well, there are n nth root to unity, so summing it up n times cancels out the n inverse, and what's left is ZA hat of R. So it's just a little bit of algebra happening. We're just subtracting something from G so that G sums to ZA hat of R if and only if the thing, Q sums to zero. So that's it. So you apply univariate sum check to this Q. That entails the prover committing to yet another quotient polynomial, actually two of them, I guess, a quotient and a remainder. And the verifier at the end of univariate sum check has to evaluate like two different polynomials at a random point, one of them being this Q, and the other being just derived from this quotient and remainder that the prover committed to during univariate sum check. So the only remaining thing to discuss is, so the verifier needs to, at the end of univariate sum check, evaluate Q at a random point R, which requires evaluating G at R. And remember, G is a hat. Sorry, let me call this point R prime. Remember, G was a hat of R, comma R prime, times Z hat of R prime. Okay, so that is at the end of the univariate sum check protocol, the verifier has to evaluate G at a random point R prime, and that requires evaluating A hat at a random point and Z hat at a random point. Now, Z hat was committed, so the verifier can get that evaluation from the commitment scheme used to commit to Z hat. And what's left is to get the evaluation of A hat at a random point. And here the situation is exactly the same as it is in Spartan, which is if the R1CS constraint matrices have repeated structure, then this evaluation, the verifier will be able to do on its own quickly. And if not, and Marlin is actually targeted at the case where there is not repeated structure. If there's not repeated structure, what you can do is you can have an honest party called the indexer in the Marlin paper cryptographically commit with a polynomial commitment scheme to A hat in pre-processing, so that way the untrusted prover can provide A hat at the necessary point to the verifier along with an evaluation proof, in the online phase. And here you have this subtlety that typically the constraint matrices A, B, and C are sparse, meaning most of the entries of A are 0, which means you'd really want to commit to A hat with a sparse polynomial commitment scheme, which means that the time to compute the commitment and evaluation proof should be proportional to the number of non-zero entries of these matrices instead of the total number of entries of these matrices. So time to commit to A hat and produce an evaluation proof is proportional not to the total number of entries, which is n squared, or really m times n, but we were assuming throughout that m equals n for simplicity, but rather just to the number of non-zeros in the matrix, non-zero entries. Okay, and so Marlin gives a sparse polynomial commitment scheme for bivariate polynomials like A hat. And the book describes it. So you can go ahead and read it if you'd like. In my opinion, sparse polynomial commitment schemes are really important and practical. So I do plan to spend some time covering how they work sometime in the next few weeks. I have some new work coming out that uses them to achieve something interesting. So I think there's actually a misperception that sparse polynomial commitment schemes are very expensive, and also that they have different amortization properties than standard polynomial commitment schemes, when in fact they have the same amortization properties, because the way sparse polynomial commitment schemes work is they kind of take a standard polynomial commitment scheme and apply it. They kind of just build on top of it. The way they're constructed is kind of through a transformation of a standard polynomial commitment scheme into a sparse polynomial commitment scheme. So they in fact have the same amortization and batching properties as the standard polynomial commitment schemes that they invoke. And yeah, so I think that there's this belief that if you can avoid a sparse polynomial commitment scheme, you should, because they're expensive and some people seem to think they have bad amortization properties. In fact, I think the opposite is true. I think they are not that expensive, and they have good amortization properties. So I'm hoping to clarify these points soon, and I think it's worth covering in the reading group. So that'll be for a future session, maybe in a few weeks or something like that. So yeah, I am not going to cover today Marlin's sparse polynomial commitment scheme. It's actually much more complicated than anything else in Spartan. So as far as I'm concerned, we now understand Marlin in full. I've started saying Spartan because Spartan also gives a sparse polynomial commitment scheme that's related to, but not quite the same as Marlin's. So that's why I started misspeaking and saying Spartan. A Spartan sounds like sparse. So apologies for the brain lapse there. Yeah, so that's Marlin. So to just kind of summarize very briefly how the protocol works, right? The prover begins by committing to the z hat, the low degree extension of the witness vector z that the prover claims to know. as well as the low degree extensions of A times Z, B times C, and Z times C. And then the prover just checks that the latter three polynomials like are indeed what they should be, which it does by invoking univariate sum check, and then kind of assuming that it's already confirmed that ZA hat, ZAB, ZB hat, and ZZ hat are what they should be. It's quite straightforward to check that Z indeed satisfies all the constraints. And that actually, you don't even need the full power of univariate sum check. You just send a quotient polynomial that allows the verifier to confirm that this expression that I'm circling here is divisible by the vanishing polynomial that maps a point R to R to the n minus 1. And that is Marlin. And to just summarize one last time, kind of the pros and cons, it gets shorter proofs than something based on the standard sum check protocol because it's only like 2 rounds, and the prover commits to a constant number of polynomials in each round. So if you use like KZG commitments where the commitments and evaluation proofs are constant size, you wind up with constant size proofs. So that's really nice. The downside is that the prover has to commit to a lot more stuff and also do some FFTs in there too. So the prover is slower. So it's just kind of a direct kind of tension between better verifier costs and worse prover costs. Okay, so that is Marlin. I can stick around if anyone wants to ask some questions, but otherwise, thanks for sticking around for the full 90 minutes. And next week, we'll probably talk about front ends and maybe start discussing lookup arguments, I guess, because I consider that to be in the purview of front ends. And it's related to these sparse polynomial commitment schemes too. So it might be a good topic to discuss next. And after that, we'll discuss how these polynomial commitments work. Okay, so thanks a lot. Let me know if you have questions. Otherwise, have a great weekend.
Thank you. Bye.
Bye.
So in Marlin, the cost is related to the non-zero entries, but in Spartan it's not.
So the situation is so Spartan applied to an instance with repeated structure will not have to commit to these matrices, the constraint matrices, in which case the prover in Spartan will only commit to the multilinear extension of the witness vector. Okay, now if the matrices A, B, and C are totally unstructured, then the Spartan prover will have to commit, if you want to at least avoid a linear time verifier, to A twiddle, B twiddle, C twiddle. And that will be the dominant cost for the Spartan prover. Nonetheless, the Spartan prover will be committing to less things than the Marlin prover. So the Marlin prover commits not only to A hat, B hat, C hat, but also to ZA hat, ZB hat, ZC hat, a bunch of quotient polynomials, right? So the difference in commitment costs between Marlin and Spartan are most accentuated when there's repeated structure in the constraint matrices, thereby saving the Spartan prover the need to commit to their multilinear extensions. But even in the case where the Spartan prover does have to commit to these multilinear extensions and give a value, I guess it's an on it, the index circuit does the commitment and the Spartan prover gives the evaluation proofs. The Spartan prover is still committing to less stuff than the Marlin prover. It's just like a less dramatic difference. Does that make sense?
Yes. What do you mean by repeated structure?
Yeah. So this gets it's a little tedious but I mean, like in the clearest sense, I really just mean that whenever A twiddle, B twiddle, C twiddle, these are the multilinear extensions of these matrices, can be evaluated quickly enough by the verifier, you don't need anyone to commit to A twiddle, B twiddle, C twiddle, right? Now, you could say, well, that's an unnatural condition. Like, I don't really know like which matrices, do or do not have multilinear extensions that can be evaluated quickly. And so the more detailed answer is like, whenever these matrices are capturing uh, it's repeated structure, yeah. So so there's a version of like data parallel, R1CS. There's also like air. Air can be expressed as so air is a kind of circuit that sort of has repeated structure baked into its definition. So if you look at the paper on CCS, customizable constraints systems, you'll see an extension of Spartan that to solve air. And so that section of the CCS paper is sort of explaining that when you take any air and you kind of look at the associated constraint matrices, the multilinear extensions are efficiently evaluatable. So whenever you have a computation that's sort of doing the same simple thing over and over again, the way any CPU execution is just applying the CPU transition function over and over again, or the way any data parallel thing sort of does the same sort of thing independently to many different pieces of data, that's repeated structure. And that's what's going to ensure that A twiddle, B twiddle, C twiddle are efficiently evaluatable. Does that make sense?
Yes, so to summarize, so if the circuit is not repeated structured, so both Marlin and Spartan needs to use sparse polynomial commitment schemes, and which will increase the which will make the cost related to non zero entries.
Yes, that's right.
And if it's structured, so there's no need for this coming.
Yes, that's it. That's exactly right. And it's yeah. So there's a paper. I don't remember. I think it's a public paper. Something about like succinct R1CS. Which is sort of just like giving a variant of Marlin where it cuts out the commitments to A hat, B hat, C hat, if in the case that they are efficiently evaluatable. And that probably works out, how you can take like any computer program and turn it into ABC for which that's the case, that they have this repeated structure. Let me see if I can find the paper, but like, yeah, I mean, everything you said is correct. Yeah, let's see. Succinct R1CS. Not coming. I wonder if this was, something that was never made public, but it would have been a follow-up to Aurora. Just Aurora's been cited so many times now. I can't really just like go through. Okay, anyway, I'll post it like in the chat or message you directly if I can find like the follow-up to Marlin that explicitly looked at avoiding the commitments to A hat, B hat, C hat in the event that there's structure. But it's kind of it's not that complicated. It's like, if there's repeated structure, then A hat, B hat, C hat can be evaluated by the verifier quickly, and so no one needs to commit to them. I mean, it's kind of that's the summary right there. Yeah, does that make sense?
Yeah. Thank you. Yeah, I don't have other questions. Just thank you and bye bye.
Yeah. Have a great weekend. I'll see you next week.
See you.
Bye.
Justin, can I just ask a quick one?
Yeah, go ahead.
Yeah, thanks. So I think in this line of work, there's also Aurora and Fractal as well. Could you just say something like briefly how they relate to Marlin?
Yeah, sure. So I think very high level, they are Marlin, but with KZG commitments replaced by Fry, and then optimizations, like concrete optimizations that make sense when the polynomial commitment scheme is Fry. Um, Very high level, that is fractal. I'm trying to remember Aurora. I remember Aurora like, yeah, okay. I think Aurora, I remember the verifier was linear time, linear in this number of non-zeros in these constraint matrices, no matter what. And that must have been because whereas Marlin gave a sparse polynomial commitment scheme, I guess Aurora must not have. So I guess Marlin came after Aurora. It's a little hazy now, and was able to get the sublinear verifier in general by giving a sparse polynomial commitment scheme so that these matrices could be committed in pre-processing, and the evaluation proofs could be produced in time proportional to the number of non-zeros. Yeah, so that's the summary. I'm pretty sure I should pull up Aurora and see if it used KZG or Fry, but it's sort of they could have used either. They made a choice. I think Aurora was supposed to be post quantum, so yeah, okay. The Aurora abstract says it's transparent and post quantum, which means they use Fry. Yeah, so that's the summary. Was that did that make sense?
Yeah, it does. Thanks.
Yeah.
Okay, yeah. So Marlin also innovated with the sparse polynomial commitment scheme, I guess. Yeah.
Yeah. So I think this is to take one more step back. I think I don't remember the timing of everything, but I think you basically had Starks for air. Okay, air, it has like uniformity like baked into the definition, like repeated structure baked in the definition. So I think Aurora was like, hey, what if we wanted to handle R1CS and not air? R1CS might not have repeated structure. In general, it's like, despite the fact that today people like air more than R1CS, back then it was like the opposite or whatever. So the goal was like, let's do something for R1CS. So you could think of Aurora as just like Starks for R1CS instead of for air. Then Marlin did two things. It gave the sparse polynomial commitment scheme so that the verifier would not be linear time in the case of unstructured constraint matrices, and it swapped the Fry poly commit for KZG to get constant proof size with the universal setup, and then Fractal took Marlin and switched the poly commit back to Fry, and that's the whole summary. Yeah.
Okay. Yeah, that's a great summary. Thank you. Yeah.
Sure.
Just one more quick one then. So you said you'll cover front ends next time. So is that the front ends material that you covered in your book?
Yeah, so that's chapter 6 of the book, and yeah, and I think most of it is pretty straightforward, except for the stuff that isn't straightforward. I think you quickly get into essentially lookup arguments. So and there is a lookup argument from a paper called Aria that is sketched in the book, but I don't think I do a great job of it. So anyway, but maybe next week I'll do like the simple part of front ends, and maybe I'll aim the week after that to do lookup arguments. Yeah, so I guess that's maybe spend a couple weeks on front ends and lookup arguments.
Cool.
So
that's good. Yeah.
Yeah, so I think if you're looking to like skip some weeks, I'd say probably next week is more rudimentary material, but then the week or two following that we'll go back to more like cutting edge stuff. Yeah, just if that's helpful.
Okay, great.
Cool.
Yeah, thanks so much. Yeah. Hope to see you next week. Yeah.
Okay, sounds good. Thanks for the questions and have a great weekend.
You too. Cheers.
Bye.